So let us finish up chapter 4. We're going to go over important and famous proofs. So here we have the last part of chapter 4, 4.6. Okay, what we learned so far? We start talking about different methods of proof and disproof. Last time we worked on example with contradiction and contraposition. We went over some examples together. Now we're going to finish this chapter by going over some important statements. The very first statement is this theorem. The theorem says, well, square root of 2 is not rational. Square root of 2 is not rational. Well, it's not rational. Okay, how do I prove that? This is a statement. Okay, you might say, well, I already know square root of 2 is irrational, but as a mathematician, how do you prove this statement? Contraposition, contradiction, direct proof, which method? Proof by So let us start proving by contradiction. So remember that when we are working with contradiction, we say, suppose not. Suppose not. Let us put this guy in a box to know that when we are working with contradiction, we always assume that the negation of this statement. Well, suppose not and square root of 2 is rational. And square root of 2 is rational. Okay. So since it is rational, remember that by definition of a rational number, so by definition, we can find P and Q, both of them are integers. The denominator is never 0, and square root of 2 is equal to P divided by Q. Q is never 0. P and Q are integers. So this is the definition. We have the definition. I'm going to also impose that this fraction is in reduced form. Let P divided by Q be in reduced form. What's the meaning of that? Remember that. Suppose you have a fraction like 4 divided by 6. They have a common factor, which is 2. If I simplify this fraction, I get 2 over 3. I say, well, this fraction is written in reduced form. They have only one common factor, which is 1. So this is reduced form. There is no common factor between P and Q. This is important. So I'm going to put this one in another box. This guy helps me to prove this statement. Okay, very well. So we know that square root of 2 is P divided by Q. Square root of 2 is P divided by Q. So let me raise both sides to the second power. It means that 2 is equal to P squared divided by Q squared. Basic algebra. So P squared is even. P squared is even. We just proved this. If n squared is even, n is also even. So P is even. We proved this last time. If n squared is even, so as n. Since P is even, so since P is even, there is an integer like k such that P is equal to 2k. Okay, perfect. So it means that P squared is 4k squared. So P squared is equal to 4k squared. Okay. So take a look at this. P squared is equal to 2k squared, and P squared is equal to 4k squared. What's the meaning of that? It means that, well, 2q squared is equal to 4k squared. It means that q squared is 2k squared. It means that q squared is even, so as q is even, q squared is even, so q is also even. P is even, q is even. It means that they have common factor 2. But we already assumed that P and Q have no common factor except for one. A reach to a contradiction. One more time. Proof by contradiction. Suppose not. Suppose not, and square root of 2 is rational. Square root of 2 is rational. It means that square root of 2 can be written as P divided by Q. P and Q are integers. They are integers, and the denominator is never 0. We also add this assumption that we reduced this fraction. This assumption helps us to reach out to a contradiction. So also suppose that P and Q have no common factor reduced form. So we're imposing a new assumption that helps us to reach to a contradiction. This is important. They have no common factor. Okay, the rest is just algebra and what we learned before. So they have no common factor. Very well. Okay. Let us do the algebra. Square root of 2 is equal to P divided by Q. It means that 2 is P squared over Q squared. What's the meaning of that? P squared is equal to 2 times Q squared. Well, it means that P squared is even. P squared is even. And by the theorem that we learned before, P is even as well. So when P is even, it means that P can be written as 2 times K. K is an integer. Okay, P is 2K. Let me put this one here. P is even. It has 2 times another integer. Very well. So P is equal to 2K. P squared is 4K squared. I'm going to type that in here. So 4K squared is equal to 2Q squared. What's the meaning of that? It means that Q squared is equal to 2K squared. It means that Q squared is even, so as Q. So Q squared is even, so as Q. But here is your contradiction. Q is even. P is also even. So Q can be written as 2 times L. As you can see, here you have common factor between P and Q, which is a raised 2. There's a contradiction with the assumption that there is no common factor between P and Q. So there is a contradiction with the assumption that P and Q have no common factors. This is your contradiction. Very well. So we just showed that the negation of the statement is false. It means that the statement itself is true. So since, I can write it this way, since not A, or the negation of the statement, the negation of the statement is false, our statement is true. So we just proved that theorem. Very good. So we are still, no, we moved on to page 2. On page 2. So here we have a proposition. The proposition says, well, 1 plus 3 times square root of 2 is irrational. Okay, perfect. Here we can say that suppose not. Proof by contradiction. This is one of the techniques of proving this statement. Proof by contradiction. Since in this section, we start talking about contradiction and contraposition, that's why we're just focusing on contradiction. You might say, hey, I want to use the direct definition and using the theorem. Yes, you can proceed that way as well. But again, since we started this chapter by moving on to contradiction and contraposition, let's use the method of contradiction. So, proof by contradiction, suppose not. Suppose the negation of this statement is true. Suppose not. And this guy is rational. Suppose not. And then negation of this statement is true. And 1 plus 3 times square root of 2 is rational. Well, okay, since this is rational, based on the definition of rational numbers, I can write 1 plus 3 times square root of 2 as p divided by q. P and q are integers. And my denominator is never 0. Well, okay. Let's just work on some basic algebras. I'm going to subtract 1 from both sides. What I get 3 times square root of 2 equals to p over q minus 1. Okay, here I can take common denominator between these two. I have 3 times square root of 2 equals to p minus q divided by q, which is still a rational number. Then I divide both sides by 3 as well. So what I have here, I have something on the numerator, which is an integer, something on the denominator, which is an integer, and note that your q is never 0. So my right-hand side is a rational number. It means that square root of 2 is a rational number? No, you just proved that square root of 2 is not rational. Since our left-hand side is square root of 2 and is not a rational number, but the right-hand side, which is p minus q divided by 3 times q is rational, we reach to a contradiction. It says, hey, you have an equality between two numbers. One of them is rational, the other one is irrational. Impossible. So we proved that the negation of the statement is false. So the statement is true. And we're done with this proof. Very well. We are moving on to page 3. So here you have a proposition. The proposition tells us that the proposition says, well, for any integer a and prime number p, for any integer like a and prime number like p, if p divides a, then, so if p is a factor of a, then p is not a factor of a plus 1. It's not a factor of a plus 1. If p divides a, P cannot divide A plus 1. Okay, which method? How do you prove this statement? Proof by So suppose we want to use method of contraposition as you suggested. So instead of proving P then Q, we prove not Q then not P. So we try to prove if P is a factor of A plus 1, then P is not a factor of A. The contraposition, you write down the contrapositive of the statement that we have, the negation of your conclusion, then the negation of your assumption. Okay, what's next? If P divides A plus 1, then P doesn't divide A. How do you proceed? Think about this and also think about proof by contradiction. Proof by contradiction. Suppose not. Suppose not. And he also divides A plus 1. So specifically recall that when we have implication P then Q, it is equivalent to not P or Q. So if I negate P then Q, it is equivalent to P and not Q. So we write down the assumption and we negate the conclusion. Remember that it says for any integer, proof by contradiction, it means that we're contradicting the whole statement. What is the negation of for all? There exists A, an integer, P and prime, such that P and not Q. What is my P? P divides A. What is the assumption? P divides A. So P divides A, and the negation of P not dividing A plus 1, P divides A plus 1. So what's wrong here? If P is a factor of A, it means that we can find an integer like K such that A is PK. If P divides A plus 1, it means that you can find another integer like L such that A plus 1 is PL. Okay, perfect. What do we have here? If I substitute A here, I get PK plus 1 equals to PL. Remember, P is prime number. So what do I get? I get P times L minus K equals to 1. Guys, P is a prime number times an integer is equal to 1. Is it possible? P is a prime number. Prime times an integer is equal to 1. This is impossible. This is the contradiction that you have. So by using the method of contradiction, you can easily prove this proposition.